Hi, Marcel here. Welcome to another video. This will be in our series about the discrete Fourier transform. Hope you're having a wonderful day. As you can see, it is daytime. I normally record these at night, but it is now the day, and it's very snowy out on the 2nd of November. Which is a bit tragic. Anyway, let's get on with life. This video and the next one will be about cyclotomic polynomials. So I mentioned in the last video that we are going to start moving on to a journey towards proving an improved Fourier uncertainty principle for ZP. And on the way to that, we have to learn about cyclotomic polynomials and then later on van der Monde matrices. Okay, so 2 videos on cyclotomic polynomials. I'm going to approach these as if you've never seen them before, but of course cyclotomic polynomials show up in all sorts of places, so maybe you've seen them before. Okay, so we are going to first define cyclotomic polynomials. Well, first we're going to have to talk about roots of unity, which we have talked about before. So let n be a positive integer, okay, and nth root of unity is any complex number omega such that omega to the n equals 1. Unity just means 1. So it's a fancy math way of saying you can think of it as an nth root of 1. Okay? Now, what does this look like? In the real numbers, of course, to have something, the power of something being 1, like a real number being 1, you either have 1 or minus 1. If it's an even number, if n is even, you could have minus 1, and if n is odd, you have to have 1. But in the complex plane, as you might know, we have this unit circle, okay? It's a really bad circle, but for example, the famous fourth root of unity, I, right? This is the complex unit, the imaginary unit, sorry, and it's a fourth root of unity because I to the 4 equals 1. Well, I squared is negative 1. That is the definition of I. And so I to the 4 is 1. So that's a fourth root of unity. Okay? So that's kind of the picture. But we can do this for any n. Now, note that if d divides n, then any dth root of unity is also an nth root of unity. So we kind of want to figure out the roots that belong to n in some sense. Like minus 1 is a second root of unity because minus 1 squared is 1, right? But it's also a fourth root of unity, right? Like so in this picture, this is minus 1. And minus 1 squared is 1, which means minus 1 to the 4 is also 1. But minus 1 to the, minus 1 should not be considered a fourth root of unity in, it's not a pure fourth root of unity in some sense. So we want to associate minus 1 to 2 and not 4. And so we have this definition, an nth root of unity is called primitive if it is not a dth or an mth, you can say mth root of unity for any 1 less than equal to m less than n. So any smaller, strictly smaller n. Okay? And you can kind of see that, so brackets, any nth root of unity is a primitive dth root of unity for some d dividing n. Okay, you can kind of see that from the picture. So we have, these are all the fourth roots of unity, right? So all the fourth roots of unity, but there's some special ones. First of all, there's 1, which of course 1 to the 4 is 1. And then there are these two, I and negative I. And then there's minus 1. Okay, so these are all the fourth roots of unity, but only the blue ones are primitive fourth roots of unity. The green one is actually a second root of unity, and 1, the red one, is a first root of unity. It's 1 to the 1 as well. Okay. So you can, that's just an illustration of that statement in the brackets. Now we're going to define the cyclotomic polynomial. So definition. I realize I don't always put this def before I define things, but when I do, you know it's going to be a big one. The nth cyclotomic polynomial so there you go. So we're defining, denoted, we're going to use capital phi of n, that's customary, is given by phi n of z is equal to the product over all omega, not all omega, but well, we'll see. So this is the product over omega of z minus omega, where in the product, omega ranges over all primitive nth roots of unity. Okay. So I mean, if you took all roots, then you would get a different polynomial. You'd actually get z to the n minus 1. But the cyclotomic polynomial only goes over the primitive nth roots of unity. Okay. And let's just do some examples. So phi 1 of z is well, there's only one primitive first root of unity, and that's 1, so it's z minus 1. Okay. Now, phi 2 of z, there are two second roots of unity, but one of them is 1, which we don't count because it's also a first root of unity. The other one is minus 1, so we have z minus minus 1, which is z plus 1. Okay. Now, things are a little more interesting when you do phi 3 of z. Okay, so let's draw this picture. So you have, I can never draw this circle correctly to make like the geometry work out, but okay, that's a circle. And that's kind of a third of the way along the circle, right? So let's call this omega, and this is omega squared, and of course omega to the 3 equals 1. Okay, so these are the two primitive nth roots of unity. So we want z minus omega and z minus omega squared. Okay? Now, so we'll just expand this out. So this is equal to z squared minus omega z minus omega squared z plus omega cubed. Okay, so omega cubed is just 1. And we want to figure out what's omega minus omega squared. So what's omega plus omega squared? Well, omega plus omega squared, if you look at these as vectors, okay, they're an equal distance from the real line. So when you add them together, the imaginary parts cancel out, you're going to get a real number. So what exactly is this real number? Well, it's a bad picture, but this is 60 degrees. This angle is actually 60 degrees. So the real part of omega is cosine of 60 degrees, which is a half. And so you add these two together. So same with the cosine below for omega squared. So you add them together, the real parts are a half plus a half, you get minus 1. So it's minus minus 1, which means you get z squared plus z plus, we said omega to the 3 is 1. So that's phi 3 of z. Okay, that was a non-trivial example. Let's just do one more. So phi 4 of z. Remember, the primitive and fourth roots of unity are I and negative I. So we have z minus I, z plus I. And this formula is just z squared minus I squared, but I squared is negative 1. So minus negative 1 is just z squared plus 1. Okay, so we see that we see some examples of cyclotomic polynomials. So you'll notice so far we've had all the cyclotomic polynomials being, all the coefficients are integers, and so that turns out to be a more general phenomenon, and we're going to prove that really soon. They're also all monic, which is very easy to see just by the formula, right? They all have z to, there's no coefficient in front of z. You product all of them, you're going to have no coefficient in front of the leading term. Yeah. Okay, so we're going to prove a little lemma about just the basic properties of the cyclotomic polynomials. Before we do that, we're going to define something called the von Mangoldt function. So this comes from number theory. Von Mangoldt function, we're going to use capital lambda. All the capital Greek letters are having fun in this video. Okay, and it's defined on, positive integers by, okay, so lambda of n is equal to, okay, log of p if n is p to the k, so p is a prime, so p prime, k greater than 1. So if n is a power of a prime, then you take log p, and otherwise it's just 0. So otherwise. Okay, so that's the von Mangoldt function. Remember, by the fundamental theorem of arithmetic, okay, which is a fancy name of saying that every number n can be factored into primes. So this is not an equal, sorry. This is a comma. Where's my pen? Pen's over here. Okay. N is, you can decompose it into primes, right? P1, E1, all the way up to PS, e to the s, to the power ES, where EI are greater than or equal to 1 and PI prime. Okay, so you learned that in high school. Every number can be factored into a product of primes. But you can take this, and if you take the log of both sides, okay, you get log n, okay, is equal to, this is used to be a product, but when you take a log, you get a sum of I equals 1 to s, ei log pi. And now if you stare at this really long, okay, you'll realize that this is just the sum of all d dividing n of the von Mangoldt function of d. Okay, because each of these are prime powers. Okay, and every time you run over a d, okay, that is a prime power, you'll get a log pi added to it. If you run over a d that isn't a prime power, you get nothing, okay? But that doesn't matter because there's no non-prime powers in this expression. Okay, but you get, every time there's a prime power, you get a log pi, which is lambda of d, and then that happens how many times? Well, it's e to the I times. It's however many times that prime power actually, or however many times that prime actually fits into n is what you get. Okay, so I mean, it might take a little bit of digesting, but it's not super hard. Okay, so now let's just do the lemma. And this is not like, I don't know, it's more just like a proposition than a lemma. It's like just basic properties of, it's not towards proving any specific theorem. Okay, so if n's greater than 1, the nth cyclotomic polynomial is monic. We already saw that, with integer coefficients, which we also saw in our examples, but we haven't proved yet. And we have phi n of 1 is equal to, okay, so it's 3 cases. So it's 0 if n equals 1. That's just the special case. It's p if n is p to the k, prime power. Yeah, p is prime, k is an integer, and 1 otherwise. Okay. So, well, you can see why the von Mangoldt function comes in, right? So if you notice log, if you take e to the both of these, you get that, right? E to the log p is p, and e to the 0 is 1. So so you'll notice there's going to be a log of the von Mangoldt. There's going to be log of, sorry. There's going to be e to the von Mangoldt function somewhere in this. Okay. All right. So let omega n be the set of all nth roots of unity primitive or not. Okay. Well, the set of all nth roots of unity is there. It's exactly the set of roots of this polynomial. So z to the n minus 1, right? So there are n roots by the fundamental theorem of algebra. There's n roots to this polynomial, and they're exactly the nth roots of unity, all of them. So this is equal to omega in omega n, big omega n, of z minus omega. Okay, so this is different from the cyclotomic polynomial formula because we take all roots, not just primitive ones. Okay, so since every nth root of unity is a primitive dth root of unity, for some d dividing n, okay, we can group some of the roots together to do this. So we group all the roots corresponding to their respective divisors d. So d dividing n, and if we do that, we'll get exactly this formula. So phi d of z. Okay. Now we can kind of see by induction we can peel away cyclotomic polynomials, right? If we can prove it for small, like for 1 and then 2 and then 3, or everything that divides n, we can peel away the cyclotomic polynomials. And we can get the formula. So actually both proofs, I forgot what we were trying to prove. So we're actually going to prove the this evaluation at 1 first, okay? And then we're going to prove the other one, but the proofs are quite similar. Okay, so let's prove that. So by induction, okay, we're going to prove the computation first. So phi n of 1 is equal to, so it's z minus 1 evaluated at 1, so it's 1 minus 1 equals 0. That's that special case we had above. Okay, and then let's get a new page. For n strictly greater than 1, okay, why not we divide out this phi n of 1? Well, we want to divide out phi of n. We can't divide, dividing by 0, but we divide out this polynomial and then evaluate it. So we get z to the n minus 1 over phi 1 of z. Obviously, the polynomials divide each other because 1 divides any number, n. Okay, so this is a limit. We have to take a limit because we're evaluating at 1. Or, yeah. Sorry. We want to evaluate this at 1, so we're going to, I kind of wrote this wrong, but this is, okay, we're going to evaluate this at 1 while dividing at the same time. So z to the n minus 1. I do need to fix this, sorry. It's just bothering me. So this is, it's going to be like z to the 1, okay? Yeah, there we go. And then so this is z minus 1, and then we use L'Hopital's rule to get n z to the n minus 1 over 1, and so that's n. When you plug it in, z equals 1. And so what we've just shown, okay, is that n is equal to the product over all d dividing n, d not equal to 1, of phi d of 1. Okay, so we took this whole product, z n minus 1, we took this whole product and we want to evaluate it at 1. Now if we evaluate it at 1, it's 0, right? But we want to show, so this product evaluated at 1, if you take out the part that makes it 0, which is the part corresponding to 1. This is 1 right here. Okay, then you actually get n. Okay, so that's what we've shown here. Okay, now we take log of both sides. Okay, and you get sum d dividing n, d equal to 1. Phi, log of phi, sorry. So the product turned into a sum, and you have log of phi d. Okay, and now since lambda of 1 equals 0, this sum here, which we saw log n is the sum over all d dividing n of lambda of n, but it's since lambda of 1 is 0, we actually have this. It's sum of d dividing n, d not equal to 1 of lambda n. Okay? Lambda of 1 is 0 because 1 isn't divisible by any prime, let alone prime powers or whatever. Okay, so that's d dividing n, d not equal to 1 of log d dividing n, sorry. Okay. So this is true. I mean, we've actually just shown that this is true, right? But the claim is that these are actually equal term-wise, okay? Then you get e to the lambda n is phi d of 1, or sorry, is phi e to the, sorry, this is a d. Lots of typos here. So then you would get, right, if these were equal term-wise, you get e to the lambda d is equal to phi d of 1 for all d, and that's exactly what we wanted to show up here. Okay, so the claim is that the two sums are equal. Well, let's actually just write this out. Claim two sums are equal term-wise. Okay, the corresponding d's equal each other, so term-wise. Well, what you notice is when n is prime, there are no other d's except 1 and n. So when n is prime, we are done. Okay, so log phi p of 1 equals lambda p equals log of p. Okay, and now you can work by induction. I mean, look, the induction kind of does itself, right? Because you've done it for primes. So we've done it for 1 already. Now you do it for 2, which is prime. 3 is prime. Now 4 is not prime, but it only has 1, 2, and 4. And now 2 is already done. And so the induction just does itself. I don't know if I have to write that all out. You cancel all the smaller terms, right? So like lambda 1 plus lambda 2 plus lambda 4. Okay, we've shown that it's equal to log phi 1 of 1 log plus log phi 2 of 1 plus log phi 4 of 1. Okay, that's what we've shown. And then these can cancel out, there's 0. And then lambda 2 is equal to this log phi 2 of 1 because it's prime, so we cross that out, and then those two must be equal. So those terms must be equal. Now you just do the induction, okay? Yeah, not the most rigorous, but like you can totally see it. Okay. So now that that's done, the formula is done. We need to show that the cyclotomic polynomials have integer coefficients. So again, we start. So now to show integer coefficients. Okay, so we start here. So z to the n minus 1 is equal to what have we done? So it's the same formula, but I've just written it slightly. I've skipped a step. So phi n of z is a cyclotomic polynomial, and now we have d dividing n and d strictly less than n phi b of z. Okay, now we're again going to go by induction. So phi 1 of z is equal to z minus 1, which is monic with integer coefficients. Okay, we proceed by strong induction. So now assume that for all d smaller than n, phi d of z is an integer polynomial. Okay, so we just need to show that this is an integer, a polynomial with integer coefficients, provided that we know this is integer. So we're done if we can show. We are done if we can show that in a factorization, oh my god, factorization z to the n minus 1 is equal to a0 plus a1z plus all the way up to ar z to the r, b0 plus b1z plus bs z to the s. If we factorize z to the n minus 1, and we know that all of these are integer, okay, where bs is equal to 1 and all bi in z, then all ai are in z. Okay. So it's clear that this, so it's clear first of all that bs must be 1, right? This polynomial here is monic, because we already saw that cyclotomic polynomials have to be not monic. So ar is monic. Okay. Now since b0 is integer, okay, so b0 is an integer, and a0 b0 has to have to multiply to minus 1. Okay, a0 b0 equals minus 1 implies that a0 and b0 are both equal to plus or minus 1. Okay, now assume that for some t greater than or equal to 0, ai is integral for all 1 less than or equal to I less than t. Okay, we're going by induction. We just did the base case. Yeah, sorry. I guess this should be a 0. We're really going to do this properly. Yeah, okay. Then we want to do it for t plus 1, right? So consider the coefficient of z to the t plus 1 in z to the n minus 1. Okay? Call it ct plus 1. Well, I mean, this is literally 0 or 1 because there's or 0 or negative 1, right? Oh, okay, no, it's 1, 0, or negative 1, whatever. It doesn't matter. The point is that it's integer. It is an integer. Okay, and of course we know what it is because ct plus 1 is equal to at plus 1 b0 plus at b1 plus all the way down to a0 bt plus 1. Okay, now we rearrange. So we get at plus 1 is equal to ct plus 1 minus at b1 minus all the way down to a0 bt plus 1 over b0. Okay, but b0 is just a sign, right? So it's 1 or negative 1. And by induction on t, we get at plus 1 is equal to plus or minus this thing. ct plus 1 minus atb1 minus a0 bt plus 1. Okay, and we get that that's an integer. Now, you conclude the induction on t, you get all these coefficients being integer, which means that the nth cyclotomic polynomial is an integer, a polynomial with integer coefficients, and then you induce on n to get it for all n. Okay. And so we've shown that the nth cyclotomic polynomial is a monic polynomial with integer coefficients, and it has this little evaluation at 1 in terms of a von Mangoldt function. It's e to the von Mangoldt function of the number n. Okay, or except for the case where n is 1, in which case it's 0. So we're not done with cyclotomic polynomials. In the next episode, we will prove the irreducibility of cyclotomic polynomials. So remember that a polynomial is irreducible if it can't be factored into two polynomials in the same ring. So for example, the integer polynomial is irreducible if you can't factor it into two other integer polynomials. And that's true of cyclotomic polynomials. And the proof is sufficiently intricate that it should have its own video. So that's next time, and I will see you then.